But Scott Halley, thank you so much for joining us today. He's been our most frequently requested speaker. So I'm thrilled that we got him to come on, and he's going to have a chat with us about igneous chemistry made easy for exploration geologists. So thank you so much, Scott. It's wonderful to have you.
Thanks, Jessica. I will share my screen. Okay. So here's a quick summary. Today I'm talking about fractional crystallization in different types of magma systems. And fractional crystallization is a process where crystals segregate from melt as the magma body is cooling. And the important thing about that is that as the crystals are removed from the melt, the volatiles that are dissolved in the magma become concentrated, and eventually that'll get to the stage where the volatiles reach a saturation point and separate from the melt and hopefully produce an ore body. What I'm going to do today is compare fractionation processes from high pressure hydrous melting, the types of melts that you'd see in porphyry copper environments. I'm going to look quickly at low pressure melting in mid-crustal environments. I'm going to compare both of those signatures with the things that we see in Archaean granites. And then briefly, I'll touch on fractionation signatures that you see in the chemistry of Tholeiitic melts, so in Archaean greenstones. And I have to put a disclaimer in here. I don't actually know very much about magmatic chemistry, but I don't think many other people do either. And I've been really fortunate in my career as a geologist because I have got to work on thousands and thousands of data sets from hundreds and hundreds of different deposits all around the world. And as I've gone through all of those different data sets, I've recognized that there are common patterns in the data that are particular to particular deposit types. And very commonly, the data that I see, the real data from real rocks, does not match the academic theory. So the bottom line is, don't believe what you read. Certainly don't believe what I tell you, and always question the underlying assumptions so that you avoid any cognitive bias in your interpretations. But one of the things that you should take away from today is I'm going to show you a handful of discrimination diagrams that you can apply to your own data so that you can recognize what kind of environment your magmas represent. The fractionation patterns will tell you something about temperature and pressure and water content and oxidation state, all the things that relate to the likelihood that a magma will generate a hydrothermal system and an ore body. So I'm going to start with some very basic background things in here. When we're looking at chemistry of drill core, everybody in the audience here will be an exploration or a mining geologist. So hopefully we're looking at some analyses of really altered rocks. So in order to understand what's going on with the chemistry of your igneous rocks, we need to plot immobile elements, and most of those are going to be trace elements. So just some really basic ideas. We often talk about trace elements as being either compatible or incompatible. And titanium is an example of a compatible element. So as a magma is crystallizing and the solid mineral phases are being removed from the melt, we'll see silica increasing. And if there are mineral phases that are crystallizing as that magma cools, if there are mineral phases crystallizing that accommodate titanium, then the titanium content will go down as silica goes up. And in every magma, there will be rutile or ilmenite or titanomagnetite or biotite. There'll be some mineral phase that takes up titanium. So titanium always decreases as silica goes up. Here's an example of an incompatible element. So typically the light rare earths, heavy rare earths, niobium, zirconium, hafnium, a whole bunch of things will behave in an incompatible fashion. And that means that as the silica content goes up, these elements increase in abundance. And that's because they don't have any common mineral phases that they substitute into. Sometimes we'll see an element will change behavior as the silica content goes up, as the temperature goes down. And zirconium is a classic example of that. So this is a really good type example from the Mount Reed volcanics. I'll be showing you a lot of these plots. And this is exactly what you'd expect to see in pretty much all of the granites on the east coast of Australia and all of the eruptive, felsic volcanics on the east coast. So zircon is an incompatible element until a melt cools to about 750, 800 degrees thereabouts. And at that temperature, that's the saturation temperature for the mineral zircon. So zirconium goes into zircon, obviously. And if those zircon crystals fractionate, if they're separated from the remaining melt, then the total zircon content will decrease. So there's a really interesting inflection point in here that you'll see in crustal melts at about 70% SiO2. Here's another example. This is from Cyril Schell-Machu, who's now the head of ETH in Zurich. And he did his PhD on Eocene porphyry copper magmas in southern Peru. There's something really, really distinctive and really different about porphyry copper magmas. In just about every other type of magma, niobium and thorium and lanthanum and a few other elements behave as incompatible elements. But in porphyries, it's different. In porphyry systems, these things will get to about 60% SiO2, and then they start declining. So in porphyries, there is a mineral phase that begins crystallizing at about 60% SiO2 that accommodates all of these elements that are normally incompatible. Really distinctive characteristic of porphyry copper magnets. Here's some data from Nansen Olsen and John Dillis from the Pebble porphyry copper deposit in Alaska. And that explains what we saw in the previous slide. So Nansen Olsen has done microprobe analyses of stacks and stacks of titanite grains and of zircon crystals and compared those to whole rock concentrations of rare earth elements and high field strength elements. And what is shown here is that for the full range of the rare earth suite, the titanite contains more than 2 orders of magnitude higher levels of rare earth elements than the whole rock value. And titanite also soaks up all of the yttrium, some of the zircon, lots of niobium, lots of thorium, lots of uranium. So that explains what we saw in this diagram. The really distinctive thing about porphyry copper magmas compared to all the other magma types is that porphyry coppers begin crystallizing titanite at about 60% SiO2, and fractionation of even a small amount of titanite means that these elements become relatively depleted in porphyry copper melts. Isn't that interesting? Here's another diagram. This is come from Bob Laux, and what he's plotted on this is the partition coefficients between a rhyolitic melt and different mineral phases. So what this tells you is that plagioclase doesn't take up any of the rare earth elements except for europium. As we come to lower and lower coefficients down in here, it means that more and more of these elements are substituting into these minerals. And I've plotted the experimental results on here for titanite. Now, one of the really interesting things about porphyry copper systems is that those magmas are really strongly depleted in heavy rare earth elements, and in particular yttrium. And that was always explained by the effect of garnet being a stable mineral in the source region that the porphyry magmas came from. Well, that might be true, but titanite takes up as much yttrium as garnet does. And what we've seen from Cyril's data and from Nansen Olsen's data is that yttrium behaves in exactly the same way as ytterbium or lanthanum or cerium or any of the other rare earth elements. We can clearly see that this pattern is due to titanite fractionation. So titanite fractionation will undoubtedly have a massive effect on the yttrium content in porphyry copper magmas. And that's a really significant point, which I'm going to show you in a few slides' time. So just going back to a few fractionation signatures in mid-crustal melts, and everybody will be familiar with this. This is the same data set from the Mount Read volcanics, and something that everybody will have learnt in first year geology at university is that europium substitutes for calcium into plagioclase. So as plagioclase fractionates, it preferentially removes europium relative to all the other rare earth elements. And we can measure the size of this dip in europium compared to the other rare earth elements. So if I plot, if there's no depletion in europium, this value has a value of 1. Right? So no fractionation of plagioclase, europium will plot across here. If plagioclase is fractionating, then this dip becomes larger, and we'll see a trend like this, declining europium with increasing silica. That's a classic signature of plagioclase fractionation. It's really informative to compare some elements that have different oxidation states. Here's a plot of scandium and vanadium versus silica. And both of these are compatible elements. Vanadium can have a valency of 3+ or 4+. Now, vanadium 3+ has the same behavior as scandium. It has really, really similar partition coefficients to scandium. So in a reduced magma where the vanadium is 3+, these two elements won't partition. They'll stay in the same relative proportions. But vanadium 4+ is less compatible in silicates, but more compatible in oxides. So once we have a slightly more oxidized melt, vanadium and scandium behave differently. So I can plot a ratio. Here's a ratio of vanadium over scandium plotted against the silica content. And this is a really typical pattern for mid-crustal melts. There's the same data we looked at before. So as these magmas are fractionating, the dominant control here on this ratio is magnetite fractionation. As magnetite crystallizes in the melt, it takes up vanadium at a much higher rate than other metals. So the vanadium to scandium ratio decreases. And something I'm going to show you here in a minute is that when we look at temperature, pressure, and water content, there's a small window in PT water space where hornblende crystallizes before magnetite. When that happens in an oxidized magma, the vanadium preferentially stays in the melt, but the scandium goes into the hornblende. So when we get crystallization of hornblende before magnetite, this fractionation trend goes the other way. And that's a really distinctive signature of porphyry copper melts. But it says something about the pressure conditions under which the melting is occurring. I mentioned at the beginning that titanium is a compatible element, but niobium is incompatible unless there's titanite kicking around. So normally in any kind of crustal magma, as they fractionate, titanium goes down, but niobium goes up. If titanite is fractionating, it goes the opposite way. So there's 4 or 5 diagrams that show you really distinctive characteristic of fractionation in low pressure crustal melts. Now we'll look at some differences in porphyry copper systems. This is a diagram from Bob Laux, and I guess everybody in the audience here will know who Bob Laux is, but in case you don't, Bob Laux is an igneous geochemist, and about 20 years ago, he had a sponsored research project sponsored by all the big mining companies in the world, and he was given the task of comparing the chemistry of magmas associated with porphyry copper systems and contrasting those to barren magmas. And he came up with a few diagnostic characteristics. And I think this is one of the best and most practical research projects I've ever seen. I'm a really big fan of his work. And really what I'm trying to do and what I'm trying to show today is building on the stuff that he's done. So Bob was the first guy, I think, who really recognised the increasing vanadium-scandium ratio in porphyry copper melts with fractionation. You can see here he's got some barren magma systems. So these are things that are fractionating magnetite, but these are things that are fractionating hornblende predominantly. And this is the field of all the big porphyry copper systems in the world. Bob did all of his work on unaltered rocks. So here's a data set from one of the biggest porphyry copper systems in Chile. And these were done with 4-acid digest ICP-MS. So we don't have silica. Instead of plotting silica on the x-axis, I've plotted scandium. So these things in yellow, this is part of the country rock sequence. And these things are fractionated magnetite. But the group here in red is the host porphyry. This is the thing that's got the copper mineralization. And the pink and the magenta are 2 late-stage porphyry intrusions. So these are post-mineral intrusions. But these things, you can see really clearly, these have fractionated bucket loads of hornblende, whereas the country rock things are fractionating fractionating magnetite. And this is through the middle of the ore body. So this is working on really, really altered mineralized rocks. Another thing that Bob Laux and others picked out is that porphyry copper magmas have a really high strontium over yttrium ratio. Now, I was discussing yttrium before. Everybody believes that the yttrium content in porphyry copper magmas is really low because garnet is present in the source region, and garnet is a really good host mineral for yttrium and heavy rare earth elements. And strontium is enriched in porphyry magmas because one of the characteristics of these melts is they have a really high water content, and high water content lowers the liquidus of plagioclase. So it delays plagioclase crystallizing until much lower temperatures. So because the yttrium stays behind and the plagioclase doesn't crystallize till late, porphyry magmas have a really high strontium yttrium ratio. And lo and behold, here's the same signature in a real data set from a real porphyry copper deposit. The point I was making about titanite previously is that fractionating a really small amount of titanite will remove most of the yttrium out of a melt. So this interpretation of the strontium yttrium signature being a result of a garnet stable source region, well, that might be true, but we would get exactly the same signature just by fractionating titanite. So there must be some pressure, temperature, water condition where titanite crystallization begins before plagioclase crystallization. So don't believe everything you read. This is the same data, and there's about 40,000 data points in here. So I've made the data points transparent, but the crosses in here show the median value for each of those color groups. Now, what I showed before was these ones in yellow had depleted vanadium. So these were the mid-crustal melts in the country rock, whereas the red cross in here is the median value for the host porphyry. Now, it took me a long time to realize this. I had looked at hundreds of data sets before I realized what was going on, but all of the porphyries I've worked on, the titanium content is always around 0.2, 0.3, 0.4%. They always have niobium around 2, 3, 4 ppm. They always have around 2 or 3 ppm thorium. They always have low light rare earths, low uranium. And they are way lower than the abundance of the high field strength elements in the crustal melts. Really distinctive signature of porphyry copper magnets. Okay, now I'm going to compare those signatures with what we see in Archaean granites. And I guess we've got a few people in the audience from Western Australia. There's a new project being run by the Geological Survey of Western Australia, and they are reanalyzing a bunch of their pulps, and they call it the Barcode Project because they're trying to geochemically characterize the stratigraphy in the eastern goldfields. This is another really, really cracking good research project being run by GSWA. And I'm going to show you the fractionation signatures in the felsic to intermediate rocks. And they're due for another really big data release in June, thereabouts. So keep your eyes open for this. This is really, really good. Here's a plot of scandium versus silica. And in this diagram, I've classified the ultramafic rocks in purple. All of the basalts are in green. And then I've got a suite of things going from andesites to dacites and different flavors of felsic rocks in orange to yellow to red. So I'm going to plot vanadium over scandium ratio against silica and compare it to the porphyry copper signature. Now, most of the rocks I've analysed to date are the eruptive rocks. These are lavas and volcanoclastics. The next release of the data is going to have reanalyses of most of the granites. But among this data, we can see there's a subset here in this burgundy colour that have an increasing vanadium-scandium ratio. So some of these things are fractionating hornblende and some are fractionating magnetite. And a lot of these are not fractionated at all. But we do see this hornblende signature in some of the Archaean felsic rocks. And when you see the granite data, you will see lots and lots and lots of hornblende diorites in the Yilgarn that plot in about here. So on the porphyry copper figure, they would be things around 10 to 12 vanadium scandium ratio and 65 to 70% SiO2. They're plotting way up in the porphyry copper field. Now I'll plot silica versus strontium yttrium ratio. On this diagram, the porphyry copper window is a ratio of around 50 to 100 and silica values of about 60 to 70. So the porphyry copper window sits in here, and there's a lot of intermediate composition rocks in the Yilgarn that plot in that field. And you can see these high vanadium scandium things in here, the hornblende fractionating ones, they are going nuts. So there's a much more extensive data set that was collected as an Amira project by Kevin Cassidy and Dave Champion. And again, on this diagram, the porphyry copper window is in about here. So what this diagram shows us is that there's an enormous suite of granites and volcanic rocks in the Yilgarn that are a result of high pressure melting of a hydrous source region. Really, really important. And when these kinds of magmas are in place at shallow levels in the crust, it is inevitable that they will generate big hydrothermal systems because they're such hydrous melts. That is really, really significant. We'll make another plot. Here's silica versus the europium anomaly. And Dave Champion and Kevin Cassidy subdivided. They had 5 main subdivisions of these granite types. I've picked out the 3 main ones. They had a group that they called the mafic series. They had a group they called a high calcium series. And they had a group they called a low calcium series. So the high calcium series are the things that have the high strontium-yttrium ratio, and they have not fractionated plagioclase. And lo and behold, they have really, really low niobium and low thorium and low light rare earth elements and low uranium. Oh, that's a titanite signature. And the things that have fractionated plagioclase are much more enriched in all those high field strength elements. So now we're seeing the same patterns in porphyry copper magmas and in Archaean granites. And that is the high calcium granites or the high calcium magmas where the high pressure and the high water content has suppressed plagioclase crystallization. Those things, because they're high calcium magmas, the high calcium content enables titanite to crystallize. And I should have mentioned before, titanite is calcium titanium silicate. So because there's more calcium in the melt, it's not going out into plagioclase, those magmas are crystallizing calcium titanium minerals rather than magnetite or rutile or ilmenite. And as soon as titanite starts to crystallize, it takes up all those high field strength elements. Isn't that cool? So these types of magmas we're seeing in here, some of these are oxidized, really, really hydrous with high metal carrying potential. The big difference between these things and porphyry copper magmas is that the Archaean magmas are full of CO2, but the porphyry magmas are full of chlorine. So they transport different metals. And there's one more thing about the Archaean granites. I couldn't say this in Perth and get away with it because all the orogenic gold people would try and hang me. But there's a really close spatial association between a subset of those hornblende diorites and orogenic gold deposits. And the hornblende diorites that are spatially associated with gold systems, one more signature that they have that the other ones don't is that they are strongly enriched in barium. And this is a signature that says these things were derived by melting an enriched mantle source. So there's something happening down in the mantle where there is fluid added to that subcontinental lithospheric mantle. It's added barium, it's added strontium, it's added sulfur, it's added gold. And when that source region is melted, it makes a really hydrous magma that transports gold into the upper crust. So here's a plot. This is a subset of those hornblende diorites, and these are color-coded by gold grade. So the things that are carrying gold have more than 1,000 ppm barium. And so if you're exploring in the Yilgarn, look for hornblende diorites that have a high vanadium-scandium ratio. They have a high strontium-yttrium ratio. They have relatively low niobium, thorium, and rare earth elements, and they have more than 1,000 ppm barium. Isn't that cool? So here's a summary. And the big difference here is the pressure. If we are comparing magmas that come from high pressure melting of a hydrous mafic source, then we'll see high calcium and strontium. We'll see high strontium-yttrium ratio. There will not be a europium anomaly. They'll have high vanadium-scandium ratio because they're fractionating hornblende. And the high field strength elements will have compatible behaviour. They won't be enriched with fractionation. With a mid-crustal melt, with the lower pressure, plagioclase will begin crystallising earlier. So the calcium and the strontium won't go up. Plagioclase will crystallise before titanite, so they'll have a decreasing strontium-yttrium ratio. There will be a europium anomaly. They'll crystallise hornblende later, crystallise magnetite before hornblende, so vanadium-scandium ratio will go down, and all of the high field strength elements will have incompatible behaviour. Right, so those patterns in the chemistry tell you something about the source, the pressure, the water content, and the oxidation state. Okay, next I'm going to talk about tholeiitic magmas. And I'll go through this fairly quickly because we're kind of pressing on in time a bit. This is the same barcode data set. And this is the standard kind of Jensen cation plot that everybody would use. Something I've plotted here is scandium against aluminium. And if we look, this time I'm going to not worry about the intermediate to felsic rocks. I'm going to look at the ultramafics to mafics. And what they've analysed to date in the barcode project is lots of komatiites and lots of basalts. So these are lavas. And these are things that have come from a deep mantle source all the way to the surface and been erupted without any modification. So magnesium-rich komatiites will have low aluminium because there's no plagioclase, and they'll have low scandium because there's no pyroxenes. And as we go to lower Mg numbers, the amount of plagioclase increases and the amount of pyroxene increases till we eventually get to normal tholeiitic basalts. What you'll see, once you get beyond the ultramafics, all of these magmas have roughly the same aluminium content. They all have 6, 7, 8% aluminium, regardless of whether it's plagioclase or alkali feldspars. Notice in here, there's a little population of data points that plots above this komatiite to komatiitic basalt trend. Just have a look at those. They're a bit different. So rather than looking at the major elements, I'm going to look at trace elements again because they're far more informative about fractionation processes. If I plot scandium versus chrome, these are all the komatiites in this box. These are just komatiites. So these are going from high Mg komatiites to increasing iron content. And there's a really strong linear trend in here. What it says is there's a limit to how much scandium and how much chrome can be accommodated in olivine. And the more iron-rich the olivine is, the more scandium and chrome can go into that mineral. There are some samples in here that have an excess of chrome. These things have more chrome than can be accommodated in olivines. So these are ultramafic rocks that contain chromite. And what you'll see is that they plot above the komatiite trend. These are iron enriched. Right, so these have gone through some kind of fractionation process that enables them to crystallize chromite. And if I just take a subset of komatiites from a different data set, look at the correlation between scandium and iron, chrome and iron, vanadium and iron. So all of these siderophile elements are really, really highly correlated with the thiolite component of the olivine, whereas nickel goes down with iron, but it goes up with magnesium. So nickel behaves differently to all the other transition metals. We'll just take a bit of a detour now, and I'm going to look at fractionation in Tholeiitic mafic rocks. And I'm going to show an example from the Golden Mile dolorite. So this is the longest intercept of Golden Mile dolorite that's ever been drilled. And I've plotted vanadium against depth downhole. And we can see the fractionation units in the Golden Mile sill in here. So there's a more chrome-rich bit at the bottom. It goes into leucogabbro, and then it gets to a certain point where the water content has built up to the point where it's crystallizing hornblende instead of pyroxene. Who would have thunk it? There's enough water in an Archaean tholeite that by the time it gets to about 80% crystallization, hornblende is stable rather than pyroxenes. Right? We really underestimate how much water there is in Archaean tholeiites. And it fractionates a bit more and it starts crystallizing magnetite. When it starts crystallizing magnetite, all the vanadium goes into the magnetite until it gets to a point where the last bit of melt is completely depleted in vanadium. So this big kink in the vanadium distribution here is all about magnetite fractionation. But all of this portion of the sill contains hornblende. That means it's got at least 4 weight % water. And when we look at the last bit of quartz dolorite in here, in thin section, this is full of micrographic intergrowths. So this is a eutectic crystallization of quartz and feldspar. And that happens when the last bit of melt is crystallizing in the presence of water. This is a water-saturated bit of melt right at the end. And there's some really interesting things happen when this fractionates in situ. So we've just been looking at this diagram, scandium versus aluminium for all the Archaean tholeiites. This is where a normal tholeite would plot. And the Golden Mile dolorite is absolutely stock standard normal Archaean tholeite. It's exactly the same bulk composition as London basalt. And 90% of all the Archaean greenstones in the world look like that. But there's a section in here where there's a really high aluminium content and low scandium. And that's because these rocks are chock-a-block full of plagioclase. So this plagioclase-rich zone is down in here. And there's a section in here where the aluminium content is lower, but the scandium is really enriched, and that is up in here. So the effect of fractionation here, which is really surprising, I haven't heard anybody describe this before, in the Golden Mile dolorite and in all the other fractionated sills in the Yilgarn, there's a lower zone of plagioclase accumulation before we get this more iron-rich trend at the end. The thing about fractionating tholeiites is that trends in the data are caused by segregating olivines or segregating pyroxenes or segregating plagioclase. And you can see those patterns most clearly when you look at the trace element data. So just for reference, on these following diagrams, I've taken this plot. We're looking at the background for Tholeiitic lavas and komatiitic lavas. I'm just comparing these other data sets with this group of tholeiites and this group of komatiites. Right, so here's two data sets from two different intrusion-hosted nickel sulfide systems. I won't tell you where they are, but this is the background tholeiite signal, and this is the komatiite trend. So here's a nickel sulfide system that has low aluminium but high scandium. So this is a pyroxene cumulate, and this is the host rock to a nickel sulfide system with 500 million tonnes of ore. And it's not in Australia. Here's another one. Here's the tholeiite signal. Here's the komatiite signal. And this is a series of chronoliths. So these are like magma tubes. And we can see some of these magma tubes are full of anorthosite. So this is an accumulation of plagioclase. And some of these are full of pyroxenite. So what we're seeing here is that in these nickel sulfide systems, these magmas have had residence time somewhere. Somewhere at the base of the crust or the upper mantle, these magmas have pondered for a period of time to the point where plagioclase and pyroxenes are separating. And as those minerals are crystallizing, the volatile content in the remaining melt is all the time increasing. So the water content is going up and the CO2 content is going up. One of the consequences of increasing water and CO2 content in a melt, in a residual melt, is that the accumulation of volatiles increases the solubility of sulfur. Right? So these are becoming more and more sulfur rich in that remaining melt portion. So we'll go back to this diagram. Let's just speculate about the consequences of ponding a magma and separating out olivines or pyroxenes or plagioclase. So if we start with a komatiitic melt and pond it somewhere near the base of the crust and fractionate olivine, what happens? Well, magma systems are never one-pass systems. If you park a komatiite near the base of the crust and fractionate it, it'll be replenished over and over and over. This is like a dripping tap. We'll get a recharge of more pulses of magma. And each pulse of magma will increase the temperature again, and it'll keep crystallizing out forsterite. It'll keep removing magnesium from the melt. And by removing magnesium, it's enriching iron and chrome and scandium and all those other siderophile elements, and it's increasing the volatile content. So the effect of fractionating out forsterite is magmas will move up this way. So we'll see lots of intrusion-hosted nickel sulfide systems on this diagram would plot up in here. So these are things that are fractionated forsterite. Another consequence of fractionating forsterite, it's removing magnesium, but enriching it in iron. And that makes the magmas more dense. Right? So iron-rich residual melts are much, much more dense. And there's a really interesting property here, and that is that plagioclase crystals have a lower density than iron-rich silicate melts. So by continuing with this process, eventually we'll get to a stage where plagioclase that crystallizes will actually float in those magma chambers. And it really enhances the segregation of pyroxenes and plagioclase. If we got to a point out over here, a more basaltic komatiite composition, and started crystal settling, pyroxene cumulates, then the cumulate phases will head this way, but the remaining melt will head this way. It's going to become more and more anorthositic. And if we go to a tholeiitic melt and crystallize plagioclase, then the remaining melt heads up into this iron tholeite territory. So all of the fractionation products from the komatiite to tholeite trend will plot at much more iron-rich compositions up in here. And it's really easy to pick those. And one last point I want to make here. Why is it that we get so many of these high strontium over yttrium magmas in the Archaean? And there's lots of people who say that high strontium yttrium magma, hornblende diorite, is evidence of subduction in the Archaean. Well, actually, that's not true. It doesn't prove that. What it says is that the subcontinental lithospheric mantle in the Archaean was hydrated. It doesn't mean that there was subduction. So think about other mechanisms where we might get water added to the base of the crust in the Archaean. And a lot of guys who work in mantle plume environments draw diagrams like this. They show evidence for a big volume of magma in these plume heads being trapped in the subcontinental lithospheric mantle or underplating the crust. What we've just shown with the golden mile dolorite is that a normal garden variety tholeite has enough water in it to start stabilizing hornblende once you get beyond 80% crystallization. Think about the consequences of that, right? Think about the volume of tholeite that was erupted in the eastern goldfields at 2.7 billion years. The greenstone of Kalgoorlie goes from Norseman to Aluna, and it's up to 50 kilometres wide, and the basalts in there are up to 5 kilometres thick. Imagine if a proportion of that magma actually underplated the crust and sat there and cooled. How much water does that mantle plume add to this environment? I think this high strontium yttrium signature in Archaean granites is a signature about how much water was added to this deep lower crustal environment at the tail end of a mantle plume. And think about the consequences of remelting that stuff. That's the story about Archaean gold deposits. So conclusions. This is all motherhood stuff. You know that exsolution of volatiles in fractionating magmas is a really critical process in lots and lots and lots of different mineral systems. I've shown you a bunch of trace element diagrams here that tell you what kind of fractionation processes are going on. So plot vanadium-scandium ratios against scandium or against silica if you have it. Plot strontium-yttrium ratios. Look at the relative enrichment of all those high field strength elements. Right? Are the high field strength elements being enriched or depleted with increasing silica? That tells you about whether or not titanite was present, and that tells you about the pressure environment that these things were generated from. All of those will tell you about what kind of magmas you have and whether or not they're likely to generate a hydrothermal system. And just a couple more things to finish up. This presentation is going to be available on the GeoHug website, and I'm also going to put it on my website, not with the voice, just with the slides. But there's a series of really useful references in here. And just to conclude, I see lots of people doing interpretations of magma chemistry using diagrams like this. So here's AFM diagram. So it's got iron, magnesium, sodium, and potassium. Don't use these diagrams because these elements are mobile during hydrothermal alteration and will give you really, really misleading classifications of your rocks. I see lots of people doing classifications like this. So just doing ratios and ternaries. Oh, I really don't like these. These are really ambiguous because you can get the same patterns in very different tectonic environments. But the really interesting thing here is that these diagrams were designed to compare rocks with equivalent SiO2 levels. And when you start mixing mafic and felsic rocks, these diagrams are going to fall apart. So don't use these. And who understands spider diagrams? Wow, these things are shocking. Just plot your data and get used to looking at the raw numbers and thinking about what are the expected ranges of trace element contents in particular magma types. Spider diagrams are just ugly. So that's the end of my presentation.
Thank you. Yeah, thank you so much for joining. And yeah, that was excellent. Lots to digest there. So no, that was a really good session. So thank you so much.